Well, a warm welcome to everyone joining. Thank you for being here. Get yourself ready with a notebook, maybe a notebook that you've already been using with the previous problem. Grab a pencil or a pen, whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're going to take a look at the bonus challenge, the semicircle secret from the previous video. So if you haven't checked that out, you should definitely go check that out because I have basically the solutions scribbled all over the whiteboard. So you're not ready to see that yet. First, go try the original problem. I'll post the video, link in the description. You can go check it out for yourself. Well, you can see what the challenge is for yourself. It is to guarantee a maximum area without using calculus. And I gave you a bit of a hint. We also developed kind of a nice formula for the area of the rectangle in terms of the width only. So let's remind you of what that was. We can call this A of W was equals to W over 2 times the square root of 100 minus W squared. But I'm actually going to put that back into the original, not sort of simplified form. So it's going to look like this. W times the square root of 25 minus W over 2 squared. We're going to do something quite interesting here. Now what we're going to do is we're going to use a trigonometric substitution and a trigonometric identity in order to solve what the maximum area truly would be, as well as which width would be required in order for that to happen. We did, if we recap last time, we did see that it's pretty close to 7. In fact, it would be a reasonable guess to say that the maximum area occurs when the width is approximately 7. But we're going to find the solution to this without requiring calculus, which is actually quite powerful. And here's how we're going to do it. We're going to suppose that W over 2 is actually equals to 5 sine of theta. Whoa. It's kind of a different substitution, isn't it? You might not be used to this kind of a substitution, but trust me, it's going to work out very well when we do this. Of course, that means that W itself is equals to 10 sine of theta. What is theta? Well, we'll see. We'll see. Let's use this substitution, plug that into the area equation, and then we'll have an area formula in terms of theta. So now we can call this A of theta is equals to 10 sine of theta times the square root of 25 minus 5 sine of theta squared. And when you see a theta inside of the sine, it acts kind of like an x, or just an independent variable. Now when you see a squared, that should get you to start thinking about a very important identity. It's a Pythagorean identity, which has been covered at some point. Here we go. This is going to be 10 sine theta times the square root of, well, of course, 25 minus 25 sine squared theta. If we were to factor out the 25, we would be left with 1 minus sine squared of theta. Now this should start looking very familiar indeed. Since sine squared plus cosine squared of theta or x or whatever variable you want, as long as these are matching, this equals to 1, which means that 1 minus sine squared is exactly equal to cosine squared. Aha! So we can change this entire expression because now we can pull out the 25 from the square root. That pulls out 5. And then we can also, maybe I'll do it in 2 steps, we can also pull this out, which got replaced with cosine squared of theta. So now we just have 50 sine of theta times cosine of theta. Wow. How does this help us? This is still the area formula. It's just in terms of theta now. Well, we can now use the double angle formula for sine. The double angle formula, if you forgot it, is sine of 2 theta is equals to 2 times sine of theta cosine theta. So if we kind of multiply both sides by 25, you'll see that this simply turns into 25 sine of 2 theta. And here we can really easily but precisely analyze the maximum possible value, because we know that sine has a maximum value. Just like cosine, the max value of sine of 2 theta, that is 1. I should say the maximum value of sine is 1, which means that the maximum value, therefore, for the area is 25 times 1. So indeed, the maximum area is exactly 25. So now let's answer the question about which width would ensure that. Well, when do we get our maximum value? We say that sine of x is a max whenever x is, if you remember what sine looks like, you should absolutely know what that looks like. Otherwise, you have no business trying to use a trigonometric substitution. This is when the angle is equals to pi over 2, technically plus 2 pi n, right? If you go around the unit circle completely in any direction, any number of times, you also get this repeated value because of the periodic nature of sine. So we need this input angle to be pi over 2, but careful, that means that we need sine of 2 theta to be maximal. That means that we need 2 theta to be equals to pi over 2, which of course means theta equals pi over 4. Now that is not a value for w. It does give us an angle, interestingly enough. So if you imagine the semicircle, which I'm not great at drawing, but that's my best shot, the angle of 45 degrees is exactly where the corner should hit the circle, or rather the semicircle. So that does give us a visual understanding of what's going on. Let's go back to our substitution that we made, which says that w over 2 equals 5 sine of theta. Technically, that means that w equals 10 sine of theta. And now we have a theta value. We can simply use theta equals pi over 4 to figure that w is going to be 10 times sine of pi over 4, which gives us 10 times root 2 over 2, which means that our w is equals to 5 square root of 2. Now, for those of you who don't know, that's okay. The square root of 2 is approximately 1.4142135. I think I'm pretty nerdy, so I've memorized some of these things. If we just want to multiply this by 5, it's very easy. Don't multiply it by 5. Instead, divide it by 2 and move the decimal. So that means that this is equals to 7, right? You get where I'm going with this? 707106755, that kind of thing. But we're going to move the decimal. So now we have 7.07106755, yada, yada, yada. And now you see how our value of 7, our estimation, was very close, like incredibly close, which corresponds to the area being very incredibly close to 25. when we looked at that chart. Look at how close that area is to 25. If we just got a little closer, 7.07, we would have a much more close approximation of the area of 25. So this is how you find the maximal area, in this case, without using any calculus. Fascinating stuff. So if we make the width exactly 5 times the square root of 2, which basically means that on either side, the x value, so to speak, maybe I'll just use this diagram, that means that the x value here, this would be 5 square root 2 over 2, and this point here would be negative 5 square root 2 over 2. Okay, brilliant use of trigonometry in order to solve a problem which would typically require calculus. We did it without calculus. I hope you're looking forward to taking calculus this year, and you will learn precisely how to find maximums and minimums of various different quantities. That's areas, volumes, etc. Okay, I think that's enough blab out of me. I'll catch you guys next time.